Hello, I'm Caitlin, and my grandfather is going to tell you something new about superfluid helium. What are you going to see and hear about the superliquid helium is not a documentary, but a new theory about it. You will experience that Bose-Einstein condensation will not be relevant. Liquid helium of the common isotope exhibits normal classical behavior between the boiling point at 4 Kelvin and the special transition at 2 Kelvin. Below this temperature, indicated as the lambda transition, all properties change drastically. The most notable changes are those of the viscosity, thermal conductivity, and the possibility to pass the most small leaks, the superleaks.
The usual way of describing the liquid was TISA's two-fluid model. If helium is directly below the lambda transition, so when helium turns into superfluid helium, it is pure helium-1. Helium-1 is a normal liquid. If the temperature drops gradually, helium-1 converts into helium-2. The atoms of helium-2, the superfluid component, would have been Bose-Einstein condensed. Helium-1 and 2 form a homogeneous mixture, and it just seems like there are two fluids.
According to TISA, right under the lambda transition temperature, helium would almost entirely be helium-1, the normal component of the mixture, while immediately the liquid changed into a bewildering good heat conductor. This theory denies TISA's concepts. Also, it is certainly not clear why helium can penetrate through super small leaks due to Bose-Einstein condensation. They say by tunneling, but tunneling is about energy and not about size. Here comes a postulate. In the lambda transition, in the direction of decreasing temperature, all existing helium-4 nuclei catch a K electron. The helium-4 atom has been popped into the still unknown hydrogen isotope hydrogen-4. So far, K capture has been known only as an occasional accident. With this postulate, there is a real common phase transition. It is supposed that the hydrogen-4 is the helium-1 in the two-fluid model of TISA.
Due to the extremely low temperature, the atoms hardly associate to hydrogen molecules.
If the temperature drops down to 0, the neutral hydrogen atom gradually shall further popping in by K electron capture. This creates an isotope of the hardly recognized element neutralium, and the isotope neutralium-4 has been involved. This tetraneutron is a neutralium atom without electrons. The new element gets number 0 in the list of elements. The position of neutralium in the periodic table of elements of Mendeleev in the column of the noble gases before helium. For some years, the existence of these neutralium particles have been known. This neutralium-4 is the helium-2 in the usual two-fluid model. The lower temperature, the more you get neutralium-4 at the expense of the hydrogen-4 isotope. At any temperature below the lambda transition, the hydrogen-4 and neutralium-4 form a homogeneous mixture. At absolute zero, the present helium completely has been converted into neutralium. In the two-fluid model of TISA, it seems there are two fluids for real, while the individual atoms do not change. In the hydrogen neutralium theory, there are really two different liquids between absolute zero and the lambda transition, both other than helium. The atoms can be reversed into each other by popping in or out of electrons. With increasing temperature, the popping out prevails. Superfluid helium can be named as a thermal superconductor because in a helium cryostat temperature differences do not maintain permanently. That is why it boils as evaporation. With metallic hydrogen, this phenomenon is easily understandable. Indeed, a metal is a good heat conductor.
Experimentally, it is known that helium is an electrical insulator under all circumstances. Metallic hydrogen is supposed to be an excellent conductor of electricity, perhaps even a superconductor. So a contradiction seems to arise.
Possibly the metallic hydrogen is disturbed by the presence of an electrical or magnetic field in the dewar. Such a field provides energy and it results that the hydrogen pops out to normal helium, very near the present solids. Then, an insulating layer of liquid helium is present with a thickness of several thousands of helium atoms between the metallic hydrogen atoms and the solids. In that way, the electrical conductivity is masked by the surface effect.
Because a normal electrical circuit is not feasible due to the insulating layer of normal liquid helium, there's only one possibility to test the conductivity: induce electrical eddy currents. This can cause two effects: heat dissipation and an accompanying magnetic field. We urge experimenters whether they actually want to try to induce eddy currents in superfluid helium and to try to detect the induced magnetic field. Perhaps there's still some heat inside.
If the temperature of some metals was sufficiently low, there was superconductivity. The electrical resistance was immeasurably low. Some of these metals were in liquid helium. Could the helium, be the hydrogen 4, have been the current conductor in some cases?
Nuclei of neutralium are bosons. Therefore, neutralium-4 can exhibit Bose-Einstein condensation. But that doesn't make understandable enough how the superfluid helium can penetrate and pass the smallest leaks, superleaks.
A neutralium atom has no shell electrons, and that is why it is roughly 100,000 times smaller than a hydrogen atom. This makes it clear that neutralium can pass through each hole.
As generally, when an electron jumps from a higher energy level to a lower one, the atom emits a photon. The theory cannot explain for sure why a photon is not emitted when the electron is captured by the nucleus.
Possibly the energy is stored as electrical, vibrational or rotational energy in the nucleus. The energy of the K electron relative to the hydrogen 4 nucleus is some mega electron volts.
The graph that shows the specific heat of helium around the lambda transition temperature shows the shape of the Greek letter lambda, hence the name lambda transition.
In my opinion, this graph was always misinterpreted. The net energy impact of the collective pop-in of the helium to hydrogen is visible. Who doesn't know the hydrogen and neutralium theory cannot think about it explanation, of course. As the temperature goes down from very high to very low, you see the trend to ever issue a further concentration of mass, and partly because of increasing order, or if you will, to reduce chaos among the molecules. If you start at extreme high temperatures and you cool down, you will see successively the forming of nuclei, ions, atoms, the association to molecules, gas turns into vapor and condenses to liquid, solidification, and I add to this list to pop in. This increase of density fits nearly.
Liquid helium can be solidified only if the pressure is at least 2.6 megapascal. Increasing the pressure, the density of this solid can grow more than 25%. This is amazing for a solid.
It can be understood believing in partial transition from hydrogen into neutralium. The isotope helium-3 might be expected to be able to pop into hydrogen-3, being tritium, and going on to 3-neutralium. Thank you for your attention. You too, ladies.